Mm-hmm.
Yeah, and today we have Donghyun Kim and with topic of Schubert polynomials and TASEP on the ring. Thank you.
Okay, thanks very much for the invitation, and I'll tell you about Schubert polynomials and the inhomogeneous TASEP on a ring. And this work is based on a joint work with Lauren Williams. So first, the asymmetric exclusion process, or ASEP, is an important model from statistical mechanics, which describes a system of particles on a lattice hopping left and right. And there are many variants of the ASEP, and these are studied with various mathematical approaches. For example, space-ansatz, quadratic algebras, combinatorics, Orthogonal polynomials, random matrices, stochastic differential equations, and hydrodynamic limits. And the ASEP has many applications in a broad range, including protein synthesis, trophic flow, formation shocks, surface growth, and sequence alignment. And among many variants of the ASEP, today we'll study the inhomogeneous TASEP on a ring. So let me introduce the inhomogeneous TASEP on a ring. So consider a lattice with n sides arranged in a ring, and we denote St of n to be the n factorial labelings of the lattice by distinct numbers from 1 to n. And we'll regard each number I as a particle of weight I. So you can just simply think that St of n is the set of permutations of length n. And the inhomogeneous TASEP on a ring of size n is a Markov chain with state space St of n, and at each time t, swap of two neighboring particles may occur. So if we have a particle of weight I on the left to the particle of weight j, then these two neighboring particles can swap their position with the rate rij given as follows. So if I is smaller than j, then the transition rate is given as xi minus yn plus 1 minus j. And here xi's and yi's, they are formal variables. And if I is greater than j, then nothing happens. Swap does not happen. So here's the example. If we have the state 1, 3, 2, 5, 4, then here 1 and 3, these are neighboring particles, and 1 is smaller than 3. So they can swap their position with the rate r13, which is x1 minus y3. And it becomes the state 3, 1, 2, 5, 4. And also, I did not write here, but 2 and 5. These two are also neighboring positions, and 2 is smaller than 5, so these two can also swap their positions with the rate x2 minus y1. And the interesting fact about the inhomogeneous TASEP on a ring is that it is a solvable lattice model. Cantini proved that in 2016, and we'll go over this fact in a more detail later. And this is the example for the inhomogeneous TASEP on a ring for n equals 3. So you can see 6 possible states, and this is the transition rate. And the diagram shows the transition rate between states. So for example, 1, 2, 3, the particles 1 and 2, they are neighboring, and they can swap their position with the rate x1 minus y2 becoming 2, 1, 3. And if you look at here, the state 3, 1, 2, so remember we are on the circle. So 2 and 3, these two particles are also neighboring. So these two positions can, so these two particles can swap their positions with the rate x2 minus y1, becoming the state 2, 1, 3. So I did not write the transition rate x2 minus y1. So this is the error. And once we have a transition diagrams, we can solve system of linear equations to get steady state probabilities for this process. So if we compute the steady state probabilities for this process, this is the answer. So for the state 1, 2, 3, 2, 3, 1, and 3, 1, 2, steady state probability is given as follows. And for these three states, this is the steady state probability. And you can observe that these three states are cyclically equivalent, and these states are cyclically equivalent. And from the definition of the inhomogeneous TASEP, there is a cyclic symmetry. So it is quite obvious that if two states are cyclically equivalent, then they have the same steady state probability. And we'll multiply all steady state probabilities by the same constant so that the steady state probability for identity permutation is this number. So for n equals 3, this guy is just x1 minus y1, which is here. And after that scaling, we'll call that a renormalized steady state probabilities and denote that as psi of w. Here, w is a permutation, so psi of w is a renormalized steady state probability for the permutation w. And from now on, if I say steady state probability, then I'm saying renormalized steady state probability. So for n equals 3, we have the steady state probability x1 minus y1 and x1 plus x2 minus y1 minus y2. Okay, so first observation is that psi of w is a positive polynomial in xi's and minus yi's. And the second observation, so x1 minus y1 is a double Schubert polynomial for the permutation 2, 1, and x1 plus x2 minus y1 minus y2 is a double Schubert polynomial for the permutation 1, 3, 2. And since I haven't defined double Schubert polynomials, I'll define them. So double Schubert polynomials, so they are indexed by permutations. And for the longest permutation sigma 0, for Sn, double Schubert polynomial is defined by a product of xi minus yj for I plus j no greater than n. And for a generic permutation sigma in Sn, we get double Schubert polynomial for that permutation by applying sequences of divided difference operator to the double Schubert polynomial for the longest permutation according to the reduced decomposition of the permutation sigma inverse sigma 0. And I will give you more example for the steady state probability for n equals 4. So this is the table, and there are 24 states in the n equals 4 case, but due to cyclic symmetry, it is enough to consider the states that start with 1. So the table shows 6 states that start with 1, and on the right, you see the probability. And you can see that everything is represented positively in terms of double Schubert polynomials. For more example, this is the table for n equals 5, and for simplicity, I'll set yi equals 0. And there are 24 states that start with 1, and these are the probabilities. And the notation, x raised to a vector, means that, so for example, this guy is just x1 to the 6, x2 to the 3, and x3. So you can see that probabilities are represented positively in terms of Schubert polynomials. So, product of Schubert polynomials is known to be positive sum of Schubert polynomials. And in this table, you can see many probabilities that are represented by product of Schubert polynomials, underlined probabilities. They look very nice. Monomial times product of Schubert polynomials. So we have focused on the probabilities. So we have focused on those probabilities, and our main result is an explicit formula for these probabilities. Okay, and there are two conjectures about the inhomogeneous TASEP. So the first conjecture is that the steady state probability psi of W is a positive polynomial in xi's and minus yi's. And the conjecture 2 says that the steady state probability psi of W is a positive sum of double Schubert polynomials. And double Schubert polynomial is known to be positive polynomial in xi's and minus yi's. Conjecture 2 is stronger than conjecture 1. And history about these conjectures. So first, Lam and Williams in 2010 studied this model, inhomogeneous TASEP, for ya equals 0, and made the above two conjectures in that setting. And later, conjecture 1 has been proved in the case of ya equals 0 by Arita and Malik. So they proved a formula that gives a monomial expansion in terms of combinatorial objects called multiline Qs. And this formula was previously conjectured by Ayer and Winston. And later, Cantini in 2016 generalized the inhomogeneous TASEP by putting y parameters and established the solvability, and then he made the above two conjectures. Okay, any questions for the setting so far? Okay.
What does solvability mean?
So he used integrability of the, so he used Yang-Baxter equation and some unitary equations to make the Z deformed steady state probability that is related to our usual steady state probability. So basically, it is same as integrability of the model. I'll discuss it more in a more detail later.
So I have a question too that's maybe kind of basic. So I'm not sure actually what positivity means here. So for conjecture 2, like some of your coefficients were like xi minus yi. And so
so it means that if you plug in minus yi's in the place of yi, then everything is positive.
Then everything is positive.
Yeah.
Okay.
So,
but aren't all the coefficients then just xi, some powers of xi minus yi? So is it positive in terms of, how is it positive in terms of them individually? Or is it, maybe this doesn't make sense.
What do you mean? So for example, if you see the probability here, if you shift the sign of y, then it becomes x1 plus x2 plus yn plus y2. And
okay.
Every coefficient is positive. Yeah.
I see. Okay. Thank you. Thank you.
Can you show the table? Yeah, this table for a second. So in this table, if we didn't set up y's to be 0, then at the beginning, instead of just x to a certain partition, we would have some product of x minus y's, right? But
so this guy becomes something like product of xi minus yj's.
Yes, but then I think that Andy is asking that, I mean, as far as I understand, the Schubert polynomials, they're also in the same variables as the coefficients. So we have this product in front, and then we have the Schubert polynomials, but they're in the variables that are going to be coefficients themselves. So I don't quite understand what positivity means when our coefficients are the variables themselves. Or you just know the predictable.
You're right.
Okay.
So you're right. So this statement is a slightly lie. So we have to say that it is a positive sum of double Schubert polynomial, and double Schubert polynomial for when specialized some variables to 0. So if we have some double Schubert polynomial and specialize some variable like x5 equals 0, then that makes sense. So yeah, you're right. This statement is a slightly lie. Yeah.
Okay, thank you.
And yeah, it is and even for the product of double Schubert polynomial, yeah, it is not obvious to expand them in terms of double Schubert polynomials. Mm-hmm. Okay, any questions? So now I'll explain the combinatorial objects, multiline Q, that gives an answer for the conjecture 1 in the case of y equals 0. So multiline Q. So multiline Q is an L cross N array in which each of Ln positions is either vacant or occupied by a ball. The number of balls in each row is weakly increasing from top to bottom. And we read of the type of multiline Q by a Boulipas algorithm. And this is the example of a multiline Q and the corresponding Boulipas algorithm. So first, start from the ball in the first row and label it with 1. And go below and move to the right until it missed the ball. So here is it, and label that ball with 1. And go below and move to the right until it missed the ball, and label that with 1. And these 3 balls are not matched, so we'll label them with 2 and repeat the same process. So go below, oh, there's a ball, so it's matched, and label that with 2. And here, 2, go below and move to the right. So this ball is already matched, so we skip it, and it is matched to here, 2. And for this one, we go below and until we miss the first unmatched ball, and it is 2. So this ball is not matched, so label that with 3. And we read of the type of a multiline Q by reading of the labels of the ball from the right to the left. And we regard the label of the vacant position as 4, which is 1 greater than the row numbers. This multiline Q has 3 rows. So the type of this multiline Q is 2, 2, 1, 4, 4, 4, 2, 3. And we call I Boulipas if a Boulipas starts from the row I. So the red one is 1 Boulipas, and the green pass, they are 2 Boulipas. And a vacant position in Q is called I covered if it is traversed by a I Boulipas, but not traversed by I prime Boulipas for smaller I prime. And we define a weight of a multiline Q. So let Z R comma I be the number of I covered vacancies on row R. And we define a weight of a multiline Q as follows. And for the previous example, this vacant position is 1 covered. And here it is 1 covered, and this guy is also 1 covered. So the position here is also traversed by 2 Boulipas, but this was already traversed by a 1 Boulipas. So we have one covered vacancy in row 2, and 2 1 covered vacancies in row 3. So this becomes the weight of a multiline Q. And theorem of Arita-Malik says that the steady state probability psi of W for the inhomogeneous TASEP is proportional to a weighted sum over multiline Q subtype W. So this is a beautiful formula, but has some limits. So we cannot deal with the model with general yi's. Actually, it is an open problem to put y parameters in the previously defined weight of the multiline Q. And it is very hard to explain the appearance of Schubert polynomials except for a special case. And for that special case is the inverse of Grassmannian permutation. So we have shown that if W is an inverse of a Grassmannian permutation that starts with 1, then there exists a weight-preserving bijection between multiline Qs of type W and certain flagged semi-standard Young tableau. So flagged means that there are bounds for each row when filling semi-standard Young tableau. So the consequence of this theorem, so the steady state probability for psi of W for the inverse of a Grassmannian permutation is proportional to a certain flagged shear function. Summing the weight over a flagged semi-standard Young tableau is a flagged shear function. And flagged shear functions are Schubert polynomials for certain vexillary permutations. And vexillary permutation means 2, 1, 3, 4 avoiding permutations. And I will define apparent avoidance. So we say that a permutation pi avoids a pattern sigma or sigma avoiding if pi does not contain a subsequence in the same relative order with sigma. So here's the example. The permutation 1, 4, 2, 6, 3, 5, 7 is not 2, 1, 3, 4, 2, 1, 4, 3 avoiding because 4, 2, 6, 5, they are in the relative position in 2, 1, 4, 3. And here is the bijection. In this case, bijection is quite simple. So on the left side, the figure shows a multiline Q of a type 1, 2, 7, 3, 8, 4, 9, 5, 6, which is an inverse of a Grassmannian permutation. And multiline Qs of this type is known to be in bijection with a flagged semi-standard tableau of this shape, and the bounds are given as 6, 6, 7, 8. So basically the bijection, if you look at the one bully path, you can fill the first row of the tableau. And if you look at the 2 bully paths, you fill the second row. And looking at the 3 bully paths, you fill the third row. And looking at the 4th bully path, you fill the 4th row of the semi-standard Young tableau. So let's look at the first one bully path. So if you look at the one bully path, horizontal step happens in the 4th row. This is in the 4th row. We fill the first row of the tableau with 4, and for the remaining boxes, we fill them with 1. And if you see 2 bully paths, then horizontal steps happen in row 3 and row 6. So fill the second row of the tableau with 3 and 6, and remaining position is filled with 2. And so on for the 3 bully paths and 4 bully paths. So in this case, bijection is quite straightforward. And actually, this is all we can get by using combinatorics of multiline Qs. So to deal with general Y parameters, we need more powerful tool, which is a solvability or integrability of the inhomogeneous TASEP. So Cantini introduced a family psi of WZ that recovers the steady state probability psi of W by taking the leading coefficient in Z variables. So taking the leading coefficient in Z variables, we can regard that the same as specializing to Z equals infinity. And we'll call psi of WZ Z deformed steady state probability. And I'll summarize how we found that family. So let V be a vector space with formal bases E1 to En, where EI represents the particle type I. And consider the n copies tensor product of V. And we can represent each state of the inhomogeneous TASEP as a basis of this space. So for example, the state 1, 3, 2, 5, 4, this is represented as this vector. And let Wn be the subspace of this n copy tensor product spanned by basis elements that represent possible states of the inhomogeneous TASEP. So basically, Wn is n factorial dimensional vector space. And let M be the Markov matrix of the inhomogeneous TASEP acting on Wn. And we can decompose the Markov matrix M as the sum of logarithms Mi. So basically, Mi is the part that records the transition of the inhomogeneous TASEP happening between neighboring positions I and I plus 1. So Mi acts locally on this part. And his idea is that suppose we have an operator Ri, A, B for formal variables A and B acting locally on this part that satisfies if A equals B, then it acts like an identity. And if we differentiate with A and plug in A equals B equals infinity, then it is proportional to the local Markov matrix Mi. And he also assuming a vector psi of Z. So this vector is indexed by a basis of Wn. So this is length n factorial vector. And if that vector satisfies this equation, so acting with Ri, Ji, plus 1 is same as swapping variables Zi and Zi plus 1. So we call this an exchange equation. So suppose we have an operator Ri and a vector satisfying the exchange equation. He showed that if we specialize the vector in Z equals infinity, then that vector is proportional to the steady state probability of the inhomogeneous TASEP. And the proof is straightforward. If we differentiate the exchange equation with Zi and plug in Z to infinity, so if you differentiate this equation in the variable Zi and plug in Z to infinity, this is it. So summing over I equals 1 to n. So this guy is telescoping. So the right-hand side becomes 0 if we sum over I equals 1 to n. And sum of Mi is a Markov matrix. So we have Markov matrix times a vector equals 0. And that means that that vector is the steady state probability. So Cantini found such operator Ri, B satisfying the additional two equations. So the first one is called unity relation, and the second one is called the Brady-Yang-Baxter equation. So in the exchange equation, you can see that Ri acts like the simple transposition. So these two conditions are actually necessary for that. And he showed the existence of the vector as the common eigenvector of a scattering matrices defined below. And he showed that, and so it can be shown that scattering matrices Si and Sj, they commute. This comes from the Brady-Yang-Baxter equation here. And from the commutability of these matrices, he showed that they have common eigenvector, and then eigenvector satisfies the exchange equation. So this is his idea, and he also proved that the exchange equation has a unique polynomial solution up to a multiplication by a symmetric function of z. And I'll show you and how we actually compute the solution. So this is the initial condition. Psi for the identity permutation, z is, so the initial condition is defined as follows. And if we expand the exchange equation component by component, gives the following. So psi of Si of W, z, is given as psi of WZ, and we apply isobaric divided difference operator. So this is possible when Wi is greater than Wi plus 1. So basically we can get psi of Si W by applying operator to psi of W. And isobaric divided difference operator, it looks like our usual divided difference operator in z variables, and so multiplied with some factor. And the nice thing is that we can compute every component of psi of W from the initial condition by applying sequences of isobaric divided difference operators. So let's look at the example for n equals 3. So for the identity permutation, psi of W, psi of identity Z is given as follows. This is the initial condition. And in the 1 to 3, these are increasing. So it seems that there is no place to apply isobaric divided difference operator. But remember, we are on the circle. So 3 and 1, they are neighboring. So we'll apply the isobaric difference divided difference operator there. So swapping 3 and 1, we get psi of 3 to 1 z by applying the isobaric divided difference operator to the initial condition. And after the computation, this is the result. And 3 to 1 is a longest permutation, so we can get to any permutation. And let's take the leading coefficient. So leading coefficient is here. In this case, x1 minus y1. And leading coefficient in z variables is here. x1 plus x2 minus y1 minus y2. So psi of the identity permutation is x1 minus y1, and psi of 3 to 1 is x1 plus x2 minus y1 minus y2. We have already seen this before at the beginning of the talk. So now I'll introduce our main result. So we say that the permutation W is evil avoiding if it starts with 1 and W avoids 4 patterns: 2, 4, 1, 3, 3, 2, 1, 4, 4, 1, 3, 2, and 4, 2, 1, 3. And we say that W is in ST of n, k if W is evil avoiding and W inverse has exactly k descent. And we showed that if W is in ST of n, k, then the steady state probability psi of W is given as a trivial factors times product of k double Schubert polynomials. And I want to say what trivial factor, but there is a simple combinatorial way to read off the trivial factor by looking at W. So this is the example. So if we have the permutation 1, 2, 5, 4, 3, then it avoids these 4 patterns. And W inverse is also 1, 2, 5, 4, 3. And this has 2 descent, 5 to 4 and 4 to 3. So W is in ST of 5, 2. So in this case, the steady state probability is given as trivial factor times 2 Schubert polynomials. And of course, there is a way to decide which permutation appear here. And we showed that the number of evil avoiding permutations in Sn is this number. And previously, the formula for n states were known by Cantini. So Cantini gave an explicit formula for psi of Wz for the permutation W of the form Wn, h. And we'll present an explicit formula for psi of Wz for evil avoiding permutations. And of course, evil avoiding permutations include this family. So to do that, we introduce Z Schubert polynomials, which we say S n lambda. And actually, the name Z Schubert polynomial can be a little bit misleading because this is indexed by a partition, not a permutation. And before defining Z Schubert polynomials, we introduce an equation of double Schubert polynomial that seems to be new. So we say code C of W of a permutation W in Sn. So C of W is an integer vector, A1 to AN, such that AI is the number of Wi greater than Wj for j greater than I. So this is the example. The code of the permutation 5, 1, 3, 4, 2. So for the first one, 5 is greater than these 4. So the code for the first part is 4, and 1 is the smallest one, so it should be 1. And for 3, 2 is smaller than 3, so 1. For 4, 2 is smaller than 4, so it's 1. And the code for the permutation 1, 3, 4, 2 becomes 0, 1, 1, 0. And this is the proposition. So let's say W and W prime. So they are permutations such that if we say the code of W is C1 to Cn, then the code of the code of W prime is given as some number m, and the rest are the same as the code of W. And if m is sufficiently big, I'll not exactly say what that means. If m is sufficiently big, then we have double Schubert polynomials for W prime is represented as a product double Schubert polynomial for W with x variables shifted. So the notation here means that we plug in x2 in the space of x1 and plug in x3 in the space of x2 and so on. And there is some factor. And this is the example here. So the permutation 5, 1, 3, 4, 2. So we computed the code here, and permutation 1, 3, 4, 2. We computed the code here. And here, in this case, 4 is sufficiently large. So we have this equation by applying the proposition. So I don't think this equation was in the literature, and the proof uses a reduced pipe dream formulas of double Schubert polynomials and combinatorics of reduced pipe dreams established by Bellary and Bergen. Okay, then now I'll introduce Z Schubert polynomials. So we say that a partition lambda is valid for n if lambda is properly contained in a length lambda cross n minus length lambda rectangle. And it is an exercise to show that valid partitions are in bijection with Grassmannian permutations. And we define Z Schubert polynomial as n of lambda if lambda is valid for n. Then Z Schubert polynomial is defined recursively from Sn minus 1 of lambda prime, where lambda prime is the partition obtained by dealing the first part of lambda. So if lambda has only one part, then lambda prime is an empty partition. Then we regard this guy as 1. And this is the recursion relation. It's quite complicated, so I will not go into the detail about this, but for the notation, sigma a of z, it means that we shift indices of z variables by a. And multiplicity of a partition is the number of the first part repeated in lambda. And the properties of Z Schubert polynomial is that if we take the leading coefficient in Z variables, then it is a double Schubert polynomial for a certain permutation. And of course, there is a rule to get a code of that permutation, indexing double Schubert polynomial. So here's the example. If we consider this Z Schubert polynomial and take the leading coefficient in Z, then it is a double Schubert polynomial for 1, 3, 4, 2. And Z Schubert polynomial here, taking the leading coefficient, gives double Schubert polynomial for this guy. And I want to say that recursive construction of Z Schubert polynomials is consistent with the equations of double Schubert polynomials. So here's the equation of the double Schubert polynomial. So double Schubert polynomial for 1, 3, 5, 4, 2 is obtained by applying divided difference operator, partial 1, partial 2, to double Schubert polynomial 5, 1, 3, 4, 2. So if we apply partial 1, then it becomes 1, 5, 3, 4, 2. And then applying partial 2, it becomes 1, 3, 5, 4, 2. And the equation here is the one that I showed you before in the proposition of double Schubert polynomials. And if we write out this complicated recurrence relation for Z Schubert polynomial, this is it. So you can see that these two equations are consistent. So it has some extra Z factors, and this guy does not affect the leading coefficient in Z variables. So again, our main result. So let's say W is in ST of n comma k, and let's say that the code of W inverse is C1 to Cn. And by the definition of ST of n comma k, W inverse has k descent. And we will denote that descent positions by A1 to AK. And we will define k partitions, lambda superscript I, for I from 1 to k. And this is the definition. So for the example, so for the permutation 1, 2, 5, 4, 3, this is in ST of 5, 2. And if we compute the two partitions, then the first partition is 2, 2, and the second partition is 1, 1, 1. And our main theorem says that if W is in ST of n, k, then psi of WZ is given as trivial factor times product of Z Schubert polynomials. Here it says, so the notation sigma means that we cyclically shift Z variables. So I did not exactly say what TI is, but roughly speaking, psi of W is given as trivial factor times Z Schubert polynomials with properly shifted Z variables. So if we take the leading coefficient of this equation, then taking the leading coefficient gives psi of W. And if we take the leading coefficient of the Schubert polynomials, it is double Schubert polynomials. So taking the leading coefficient gives our main theorem. So the proof idea is that we first prove the theorem for ST of n, 1. And these are precisely the set of inverse of Grassmannian permutations that start with 1. And next, we apply factorization theorem by Cantini. So he generalized the factorization theorem of psi of W, which was proved using multiline queues. And for the future directions, it would be interesting to give a combinatorial formula for the Z Schubert polynomial. So far we defined it in terms of recurrence relations. So leading coefficient is a double Schubert polynomial for a vexillary permutation. So it has a combinatorial formula in terms of flagged semi-standard Young tableau. So hopefully, if we can express this Z Schubert polynomial as a weighted sum over flagged semi-standard Young tableau, that would be very nice. And also, we can hope to put beta parameters in the inhomogeneous TASEP so that Schubert polynomials that we see lift to beta cross-centric polynomials. And it would be nice to define Z Schubert polynomials in a more general setting and understand psi of WZ for W other than evil avoiding permutations. So far, we only understand psi of W for evil avoiding permutations. And I checked that this is possible for the probability that is the sum of two Schubert polynomials. And so the probability has Schubert positivity, so it might be possible to find a geometric interpretation in terms of Schubert varieties. Okay, this is all. So thanks for your attention.
Okay, thank you so much.
Mm-hmm.